Neuromorphic computing is a relative new field of computing that is based on the structure and function of the human brain. It aims to create computing systems that are more energy efficient and capable of handling complex tasks such as perception, decision making, and learning, in a way that is similar to how biological neurons process information. The human brain is a remarkable computing machine that can process vast amounts of information with remarkable efficiency. It is estimated that the human brain contains over 100 billion neurons and trillions of synapses, each performing a specific function in processing information. The structure and function of these neurons have been the subject of much research and study, and researchers in the field of neuromorphic computing aim to replicate these structures and function in artificial computing systems. In traditional computing systems, information is processed by a central processor that follows a set of instructions stored in memory. However, this approach has limitations in terms of energy, efficiency, and scalability. Neuromorphic computing, on the other hand, is based on a distributed architecture where computation is performed by many simple processing elements that are interconnected in a network. The key element of neuromorphic system is the artificial neuron, which is a computational unit that mimics the behavior of biological neurons. Artificial neurons receive inputs from other neurons or sensors, perform simple computations, and generate outputs that are transmitted to other neurons or actuators. The interactions between these neurons determine the behavior of the system as a whole. One of the key advantages of neuromorphic computing is its ability to perform complex computations using very little energy. This is because artificial neurons require much less power to perform their computations than traditional digital circuits. This low power consumption makes neuromorphic computing particularly attractive for applications in embedded systems and the Internet of Things, where energy efficiency is critical. Additionally, neuromorphic systems can be more resilient to environmental factors such as temperature and power fluctuations, as they rely on a large number of simple processing elements rather than a single central processor. Another advantage of neuromorphic computing is its ability to process information in real time. Traditional computing systems often rely on batch processing, which can cause significant delays in time-critical applications. Neuromorphic systems, on the other hand, can process information as soon as it becomes available, making them well-suited for applications such as autonomous robots, wearable devices, and the other real-time systems. In these applications, the ability to process information quickly and respond to changing conditions is critical, and neuromorphic systems offer a unique advantage in this regard. One of the challenges in developing neuromorphic systems is the lack of standardization in the field. Different research groups have developed different types of artificial neurons, each with its own set of characteristics and limitations. This makes it difficult to compare and integrate different systems, which slows down the development of the field as a whole. However, researchers are working to develop standardized platforms for neuromorphic computing, such as the spiking neural network architecture and the Loihe chip from Intel, which will help to accelerate the development of the field. Another challenge in developing neuromorphic systems is the lack of large-scale datasets that can be used to train these systems. Unlike traditional machine learning systems, which rely on large datasets to train their models, neuromorphic systems are typically trained using much smaller datasets. This is because the structure and function of biological neurons are not yet fully understood, and more research is needed to develop better models of these neurons. In addition, traditional machine learning algorithms are not well suited to neuromorphic systems, as they require a large number of parameters to be optimized, which is not possible in a low-power system. Despite these challenges, neuromorphic computing has the potential to revolutionize the field of computing by offering a new approach to processing information that is more energy efficient, scalable, and capable of handling complex tasks in real time. This has the potential to impact a wide range of industries, including healthcare, finance, transportation, and defense. For example, in the healthcare industry, neuromorphic computing can be used to develop wearable devices that can monitor a person's health in real time, alerting healthcare providers in case of an emergency. In finance, neuromorphic systems can be used to process large amounts of financial data in real time, allowing traders to make more informed decisions. In transportation, neuromorphic systems can be used to develop autonomous vehicles that can make decisions and respond to changing conditions in real time. In defense, neuromorphic systems can be used to develop advanced sensors and algorithms that can detect and respond to potential threats. One of the most exciting areas of application for neuromorphic computing is in the field of machine learning. Neuromorphic systems can be used to train machine learning models that are much more energy efficient and scalable than traditional machine learning systems. This has the potential to revolutionize the field of machine learning, making it possible to develop systems that can learn from data and make predictions in real time, even in low-power embedded systems. In conclusion, neuromorphic computing represents a major advance in the field of computing. By mimicking the structure and function of the human brain, neuromorphic systems offer a new approach to processing information that is more energy efficient, scalable, and capable of handling complex tasks in real time. While there are still many challenges to be overcome in developing these systems, the potential benefits are enormous and the field is rapidly advancing.